S-35 has officially completed a crucial and successful test in preparation for Flight 9. While there was a slight delay, it looks like the countdown is finally beginning. Meanwhile, big milestones have reached across the board. OLM-2 has been fully stacked at Pad B, Booster 14 has arrived at the launch pad, and Test Tank 17 has also taken an important step forward. And on the other side of the world, China is preparing to launch the next module to expand its Tiangong space station. Let's dive into all the latest developments in today's episode of Great SpaceX. In the previous episode, we saw S-35 roll out to the Massey Test Site after undergoing an engine swap. However, the initial test attempt on May 11th was unexpectedly aborted due to an unspecified issue. Despite that setback, the SpaceX team quickly regrouped and pushed ahead without hesitation. Just a day later, on the morning of May 12th, SpaceX initiated another static fire test with S-35. As usual, the vehicle underwent full fueling procedures. The venting from the tanks and vehicle indicated that both liquid oxygen and methane were being loaded. While the methane load was lower than liquid oxygen, it was noticeably higher than in prior tests, hinting at a longer and more intensive test ahead. And that's exactly what happened. Once all systems were checked and ready, the engines roared to life. The thrust was redirected through the flame trench system designed to protect the test stand and hardware from damage. From the visual output, thick dust clouds and intense engine flames, it's estimated that all 6 engines successfully ignited, producing roughly 1,400 tons of thrust. What stood out the most during this test was its duration. Based on footage and visual cues, the engines appeared to fire for a full minute, making it the longest full-duration static fire for a Starship upper stage to date. For comparison, the previous record was held by S-34, which approached the 1-minute mark, but S-35 clearly crossed that milestone, setting a new benchmark for upper stage testing. Throughout the test, observers noted that the engines seemed to go through thrust variation cycles. This likely served to test the flexibility and range of the engine system, pushing them closer to real flight conditions. Toward the end of the test, it appeared the vacuum engines shut down first, possibly simulating the shutdown sequence expected during descent and landing procedures in flight. Following engine cutoff, the standard detanking process began, with frost visibly receding from the vehicle. There were no public reports or signs of any malfunction, which strongly suggests the test was successful. It's yet another testament to SpaceX's ability to rapidly diagnose and resolve technical issues under pressure. After the brief doubts raised by earlier setbacks this month, S-35's successful long-duration burn confirms that progress is solidly back on track. Although it's not confirmed whether SpaceX will conduct a follow-up test with a single engine, plans are clearly moving forward. Shortly after the successful static fire, a road closure notice was issued for May 13th from 10 in the morning to 4 p.m., marking a return route from Massey back to the factory. This all but confirms that S-35 is heading back to Mega Bay 2. There, it will undergo post-test inspections with special focus on the engine section. As the engines have been a critical issue on the last 2 flights, verifying their integrity is essential. In addition to engine checks, SpaceX will likely install the flight termination system and integrate the payload. Once complete, S-35 will be rolled out to the launch pad where it'll be paired with B-14. Speaking of B-14, that booster has also taken key steps forward. On the morning of May 12th, its transport stand was delivered to Mega Bay 1. By that afternoon, B-14, topped with its signature crown, departed the Mega Bay en route to the launch pad. It has now officially arrived and is awaiting integration. The coordinated movement of both S-35 and B-14 highlights how quickly things are ramping up. The next big milestone, Flight 9, is drawing near. While earlier projections hinted at a mid-May launch, the latest updates from the FAA suggest the launch will take place no earlier than May 21st. Although this represents a slight delay, it's clear SpaceX is taking the extra time to ensure everything is thoroughly tested and mission ready. So, are you ready to witness Flight 9? If so, type "here we go" in the comment section down below, and don't forget to like the video and subscribe to our channel so you never miss a moment of SpaceX's incredible journey. Beyond the excitement of the upcoming launch, SpaceX is also making significant progress on long-term infrastructure and vehicle development, particularly with Pad B and the next-generation Starship V3. At Pad B, following the initial lift test on May 11th, the full installation of the orbital launch mount took place early on May 12th. Using two massive yellow cranes, SpaceX successfully lifted the OLM and positioned it atop the core structure of the launch pad. This milestone marks the completion of Pad B's foundational build, a process that has unfolded over the past year. Starting with the construction of the tower base, SpaceX steadily assembled the tower sections, built the flame trench and flame deflector system, installed the tank farm, and finally integrated the OLM into the pad's framework. With these major components now in place, Pad B is transitioning into the testing phase. A full system checkout is expected soon, and it will likely involve integration with a Starship prototype. The leading candidate for this role appears to be Test Tank 17, which has recently been involved in several important steps. Alternatively, the pad may also be used to support static fire testing for full Super Heavy boosters, such as B-15, B-16, and B-17. Once testing confirms the reliability of the new pad, Pad B will begin supporting actual missions. This could include a dramatic milestone, the first ship catch attempt, potentially during Flight 10. Following that, Pad B is expected to be used for full launch operations, beginning as early as Flight 11. Pad B's enhancements, including the introduction of a mobile OLM and a dedicated flame trench, represent major steps forward for Starship's launch architecture. These innovations will improve efficiency, safety, and reusability, and they are crucial for supporting the rapid launch cadence SpaceX is aiming for. The FAA has already approved up to 25 launches per year from Starbase, with long-term goals of achieving 400 launches over the next 4 years. Given this vision, it's no surprise that SpaceX is already working on similar upgrades at its Florida launch site. Following the removal of the previous OLM system there, SpaceX appears to be moving toward implementing the same mobile OLM and flame trench designs, creating a consistent, scalable infrastructure across its launch locations. These sweeping changes are more than just infrastructure improvements. They are setting the stage for the next evolution of the Starship vehicle itself, version 3. The V3 Starship promises to be the most powerful and advanced iteration yet. Development is already underway, with Test Tank 17 serving as the first demonstrator for this version. Currently located at the Massey Test Site, the tank was recently lifted into a small structural cage at a secondary stand, an unfamiliar setup whose specific purpose remains unclear. This could be a step in evaluating the tank's mechanical properties, structural interfaces, or thermal protection capabilities. While details are still emerging, it's evident that Test Tank 17 is only at the beginning of a comprehensive testing campaign. Additional evaluations are expected, including a possible integration test at Pad B, which will be instrumental in validating the design changes for the V3 series. These tests will feed directly into the development of the first full V3 booster, B-18, which is anticipated to begin production soon. If timelines hold, B-18 could be completed in the coming months and may even fly by the end of the year. At the same time, the first V3 ship, likely S-39, may begin stacking once space becomes available in Megabay 2. This will likely happen once S-35 is moved to the launch site or S-38 finishes its stacking process. Stay tuned, because in the coming months, the full transformation of Starship is set to unfold before our very eyes. China's ambitions in space continue to expand, and the next major step involves the further development of its Tiangong space station. Since its construction began in 2021, Tiangong has grown into a formidable space platform and a potential long-term rival to the aging International Space Station. The current configuration includes 3 core modules, the Tianhe core, and 2 laboratory modules, Wentian and Mengtian. However, this is just the foundation. From the beginning, China has outlined plans to expand Tiangong into a 6-module structure. This future design aims to support larger astronaut crews, accommodate a broader range of scientific research, and offer new opportunities for international collaboration. One of the clearest signs of this next phase came on April 30th, when Wang Jue of the China Aerospace Science and Technology Corporation, or CASC as it's also known by, confirmed in an interview with China Central Television, CCTV, that future launches of additional modules will be carried out using China's most powerful rocket, the Long March 5B. This heavy-lift rocket has already proven itself during the core construction of Tiangong, and it is now expected to play a key role in deploying new station modules. While no official dates have been announced for the additional habitation or science modules, one major mission is already on the horizon. The Suntian Space Telescope, one of China's most advanced space science missions, is scheduled to launch next year and is expected to begin operations in 2027. Suntian, often described as China's version of the Hubble Space Telescope, will be a powerful observatory in low Earth orbit. The telescope will measure 14 meters in length, 4.5 meters in diameter, and weigh around 15.5 tons. It will be equipped with a 2-meter primary mirror and a 2.5 gigapixel camera. Most notably, it'll have a field of view 300 to 350 times larger than Hubble, allowing for massive high-resolution surveys of the cosmos. Suntian will fly in the same orbit as Tiangong and is designed to dock periodically with the space station for maintenance and refueling, another example of China's long-term planning and integrated space strategy. Beyond its technical ambitions, China is also positioning Tiangong as a hub for international cooperation. Earlier this year, it announced that Pakistani astronauts are being trained to visit the station, marking what would be the first time non-Chinese astronauts participate in a Tiangong mission. Chinese space officials have also stated that discussions are underway with several other nations interested in sending their astronauts to the station. This emphasis on inclusion and collaboration could allow China to build stronger international partnerships and expand its influence in space diplomacy. To support these broader goals, China is developing a new generation of crew spacecraft. 2 versions are currently being worked on, including a partially reusable low Earth orbit variant capable of carrying 6 to 7 astronauts or a smaller crew alongside up to 500 kilograms of cargo. This flexibility in crew and cargo missions is essential for long-term station logistics, especially as Tiangong becomes more active and populated. China's steady and strategic expansion of Tiangong sends a clear message. It is building not just a national laboratory in space, but a new center of gravity for global space collaboration and exploration. The question now is how NASA and its partners will respond. Will they accelerate efforts to develop a commercial successor to the ISS, or will we see greater urgency in international partnerships and new investments in orbital infrastructure? Only time will tell, but one thing is certain, the competition in space is heating up again. Landing on a drone ship. It's a bold vision SpaceX has long had for Starship, and it's now been officially highlighted in a recent FAA document. But that leads to a bigger question. What happens next? How will Starship return home? This is a question many have been asking, and impressively, SpaceX already has a unique answer, something they're calling horizontal transportation. So why is SpaceX choosing this method? What upgrades or changes will be needed to make it work? It's been 2 years since Starship's very first integrated test flight, and now we're on the brink of Flight 9. After countless upgrades and iterations, SpaceX has just taken another major step forward. The FAA has officially approved the Starship launch proposal at Starbase. This approval marks a critical milestone. It allows SpaceX to conduct up to 25 Starship launches per year from the site without mandatory delays for mishap investigations after every anomaly. That flexibility could drastically accelerate Starship's development and testing timeline. And with the upgraded launch pad and improved vehicles ready for action, a new era for Starship may be just around the corner. Equally important, the FAA document also outlines several designated landing zones for Starship operations strategically placed across the globe. These include offshore regions near Texas in the Gulf of Mexico, locations in the Indian Ocean, and 2 areas in the eastern Pacific Ocean. Notably, many of these zones are located over open water, and that reveals SpaceX's preferred landing method going forward: ocean recovery using a drone ship. This approach is explicitly detailed in the FAA's final tiered environmental assessment, confirming that SpaceX intends to apply the same successful recovery strategy it developed for Falcon 9. As many are already familiar, Falcon boosters land vertically on drone ships positioned offshore and are then transported back to the mainland for inspection, refurbishment, and eventual reuse. It's a system that has enabled dozens of reflights and dramatically lowered launch costs. But Starship, of course, introduces a whole new scale of complexity. Both Starship's upper stage and the massive Super Heavy booster are significantly taller and heavier than Falcon 9. While Falcon boosters are around 47 meters tall and weigh approximately 25.6 tons dry, Starship and Super Heavy stand at about 50 and 71 meters tall, respectively, and those figures may increase to 70 and 80 meters with future upgrades, as referenced in the FAA documentation. This scale creates a key logistical challenge. How do you safely transport such enormous vehicles once they've landed on a drone ship? At first, many assumed SpaceX would follow the same vertical recovery method used with Falcon, but that has now been officially ruled out. Instead, SpaceX will employ a safer, more stable solution: horizontal transportation. According to the final tiered EA, after landing and safing, the breakover fixture assembly, which involves controlled supported drop from vertical to horizontal of the Starship, commence. In simple terms, this means that after a successful landing and safety checks, Starship or Super Heavy will be gently tilted from a standing position into a horizontal one using specialized hardware. This will likely involve a crane winch system or mechanical pivot designed to lower the massive vehicle safely and precisely. Why horizontal transport? Because transporting these giant stages vertically on a ship is simply too risky. Even Falcon 9, despite its shorter size and support from landing legs, has tipped over during transport on rough seas. Without legs, Starship vehicles lack the structural support to remain upright during long trips, especially when factoring in unpredictable ocean conditions. Given the sheer height and mass of Starship's components, any instability could result in catastrophic damage. Horizontal transport significantly reduces that risk. By securing the vehicle along its length, SpaceX can better stabilize it against swaying, rolling, or unexpected movements caused by waves or wind. Though this method may reduce how many vehicles can be transported at once, safety and reliability clearly take priority at this stage of development. And with no current need to move Starships in bulk, that's a trade-off SpaceX seems happy to make. Once the vehicle is placed horizontally, it'll be firmly strapped and locked into position on the drone ship's deck. Every step will be monitored and precisely executed to ensure there's no unnecessary stress on the structure during the process. It's a demanding task that will require sophisticated coordination and equipment, but it's one that promises a much higher success rate for post-landing recovery. In the long term, this approach could play a critical role in achieving SpaceX's goal of rapid reusability. It enables safe transport back to shore for inspection, maintenance, and reflight, potentially allowing SpaceX to ramp up Starship's flight cadence over time. So what do you think of this horizontal recovery strategy? Do you support SpaceX's new approach? If so, let us know by commenting "Let's do it" down below. And don't forget to like the video and subscribe to our channel for more updates as we follow every stage of SpaceX's Starship journey, from liftoff to landing and beyond. If SpaceX fully commits to transporting Starship horizontally after ocean landings, a significant amount of planning and infrastructure will be needed. To start, SpaceX must determine what kind of vessels will handle transportation. It remains unclear whether Starship stages will be carried directly on the drone ship after landing or transferred onto separate transport vessels. Either option would require a large fleet to support rapid launch cadence. For example, each designated landing region would need at least 2 operational ships, one to return a landed vehicle while the other remains in position for upcoming missions. This redundancy will be vital, especially with the FAA now authorizing up to 25 Starship flights per year, translating to roughly 2 or more launches each month. And as Starship scales up, that number will only grow. One concept that SpaceX could explore is a supersized transport vessel similar in size to an aircraft carrier. This idea was recently hinted at by John Edwards, SpaceX VP, in reference to handling Falcon Heavy boosters. A massive ship capable of holding multiple Super Heavy boosters or Starships could streamline recovery and reduce turnaround time between missions. Each drone ship or transport vessel will also need a specialized system to shift the landed vehicle from a vertical to a horizontal position. These mechanisms must be both compact and robust, capable of safely handling vehicles that weigh hundreds of tons while maintaining stability in ocean conditions. Additionally, SpaceX might integrate a deluge system similar to those used on launch pads to reduce heat and pressure effects during and after landing. The biggest challenge, however, lies in the structural demands. Starship and Super Heavy produce extreme thrust and carry enormous weight, especially during landing. These transport systems must be engineered to endure repeated impacts over long-term operations. Unlike Falcon 9, the Starship system is larger and more complex, raising the bar for both durability and flexibility. Another key design consideration is the lack of landing legs. Currently, both Starship stages rely on ground-based or tower-assisted recovery. If they are to land on a drone ship and transition horizontally, there must be a support system in place. Adding permanent legs could interfere with horizontal transport. One possible solution is a foldable landing leg system, legs that deploy for landing and retract or fold away before the vehicle is laid down for transport. This kind of system could also benefit future Moon or Mars landings, where soft surface touchdowns will be required. That said, implementing foldable legs is no small task. It would require major redesigns of the aft section, including structural reinforcements, hydraulics, and possibly rearranged plumbing or engine configurations. Finally, SpaceX will need international cooperation. While U.S. coastal regions like the Gulf of Mexico or the Pacific are within U.S. jurisdiction, other planned recovery zones, such as the Indian Ocean and regions off South Africa, will require diplomatic agreements and support from nearby countries. Australia may be a willing partner, but coordination with South American nations remains uncertain and could pose logistical or regulatory hurdles. If these challenges are successfully addressed, SpaceX could significantly enhance the potential for Starship landings on drone ships. First and foremost, landing at sea greatly increases operational safety. The ocean provides a natural buffer zone, reducing the risk to people, infrastructure, and surrounding environments in the event of a landing failure. If a problem arises during descent, the rocket can be diverted into the sea, minimizing potential damage and avoiding hazards on land. Secondly, drone ship landings allow SpaceX to optimize flight performance. By eliminating the need for a fuel-consuming return to a land-based site, more propellant can be allocated toward carrying heavier payloads or achieving higher orbits. This improves overall mission efficiency and gives SpaceX greater flexibility in designing future flight profiles. Thirdly, drone ships add unmatched flexibility to recovery operations. Because these vessels are mobile, they can be positioned virtually anywhere at sea to align with the flight trajectory. This dynamic placement makes recovery easier and more precise, particularly when launching to high-energy or polar orbits. It's a distinct advantage that static land-based landing zones simply cannot offer. SpaceX has already demonstrated the global potential of this approach by partnering with countries like the Bahamas to expand recovery capabilities. With Starship, the company is aiming even higher. As outlined in the FAA's final tiered environmental assessment, SpaceX has identified multiple offshore landing zones around the world, confirming its intention to scale the strategy for larger vehicles. Previously, the main obstacle to drone ship landings was post-landing transport, especially for massive stages like Super Heavy and Starship. However, with the adoption of horizontal transportation, SpaceX now has a safer and more feasible way to return these vehicles to shore for refurbishment and reuse. Looking ahead, this strategy could easily extend to SpaceX's operations in Florida. In fact, the FAA's environmental impact statement for Starship at Kennedy Space Center includes drone ship recovery as an approved landing method. This means SpaceX may soon implement a dedicated infrastructure for horizontally transporting recovered stages from sea to its Florida facilities. With safety, flexibility, and performance benefits all aligned, drone ship landings paired with horizontal transport could become a cornerstone of Starship's rapid reusability in the near future. The enhancement of drone ship landings will add flexibility to SpaceX's operations. With reliable sea and tower-based landings, the company can adjust based on mission type, location, or weather. Once recovery and transport logistics are optimized, SpaceX will have the freedom to push Starship higher, farther, and more frequently, bringing us closer to a truly reusable spaceflight future. So, let's watch closely and see what new milestones they'll reach next. Refueling in space. It's one of the most anticipated and critical steps in Starship's journey. For a long time, many have questioned whether this system was even possible, especially given the challenges and the pace of Starship's development. But now SpaceX has silenced those doubts with a bold new prototype, featuring a stunning design built specifically for this complex mission. All of it is focused on achieving an extraordinary milestone, in-orbit refueling like we've never seen before. So what makes this latest Starship prototype so special, and how is SpaceX gearing up for this pivotal moment in spaceflight? As many space enthusiasts know, Starship is the largest and most powerful rocket ever built. With that scale comes tremendous potential, but also enormous technical challenges. One of the biggest is fueling. Because of its size and mission scope, Starship requires far more fuel than any previous rocket, especially for missions that go beyond Earth orbit. To address this, SpaceX has been developing an in-space refueling system, essentially a way to top up Starship's tanks while it's already in orbit. The idea is simple. After Starship reaches space and uses most of its fuel to escape Earth's gravity, it'll need to dock with a second Starship, one filled with fuel, so that it can be refueled and continue its journey to destinations like the Moon or Mars. This concept isn't new. It's been discussed since Starship was first introduced. However, progress has been slow, and many have doubted whether such a complex system could actually be built. Some critics even saw it as a theoretical idea rather than a realistic engineering goal. But now, SpaceX may have just turned that skepticism on its head. On the 7th of May, sharp-eyed observers noticed a new section being moved at SpaceX's Starbase production site. This wasn't just any ordinary part, it was a unique Starship section made up of only 2 rigs. This particular segment appears to sit between the liquid methane and liquid oxygen tanks on a Starship vehicle. Most importantly, it featured something we've never seen before: 2 large valve structures, likely intended to connect with fuel lines. These could be early versions of a quick disconnect system, hardware designed to safely transfer cryogenic fuel in orbit. While SpaceX hasn't officially confirmed the purpose of this new design, many are confident that it's directly tied to orbital refueling. The placement, size, and configuration of the valves suggest a high degree of control over fuel flow, something that would be essential during a delicate refueling operation in space. This section might just be the foundation. It's very possible that more components will be added in future builds, including locking mechanisms, flow regulators, and safety systems that'll allow Starship to safely transfer fuel with high precision. Each valve likely connects to a different tank, one for liquid methane, the other for liquid oxygen. This separation isn't just logical, it's crucial. Though both propellants are stored in liquid form, they have very different boiling points, about negative 180 degrees Celsius or negative 292 degrees Fahrenheit for methane, and negative 207 degrees Celsius or negative 341 degrees Fahrenheit for oxygen. Transferring both through the same system could result in temperature imbalances, with oxygen heating up or methane freezing. By keeping these systems separate, SpaceX can more easily insulate each fuel line, reducing the risk of any cross-contamination and simplifying the engineering. This dual-valve design may also make it easier to maintain the system long-term, especially since there won't be astronauts around to make manual adjustments during refueling. Now, how might fuel actually be transferred between 2 starships in orbit? There are 3 main methods engineers often consider. The first is using mechanical pumps to move the fuel. The second involves using the controlled movement of the 2 spacecraft, essentially aligning and maneuvering them in a way that facilitates transfer. The third relies on pressure differences between the tanks, using the natural flow of liquids from high-pressure areas to low-pressure ones. Of these, the pressure method is the simplest and may be the most feasible in early testing, since it requires fewer moving parts and less complicated equipment. In the long run, SpaceX might not rely solely on ship-to-ship refueling. Another future concept is the creation of an orbital fuel depot, a floating gas station in space that starships could dock with multiple times. That could make the entire process more efficient and provide flexibility for a wider range of missions. So what does this new development mean for the timeline? Currently, SpaceX is stacking Ship 38, while S-39 is expected to be the first of the new V3 prototype line. Interestingly, the new 2-ring section with the valves appears larger than what we've seen on previous starships. However, it likely won't be part of S-39 since SpaceX needs to complete a baseline V3 before introducing more advanced modifications. That means this new part could be for Ship 40, or a future prototype built specifically for testing refueling systems. Given SpaceX's current production speed, this refueling prototype could be fully assembled by the second half of 2025, or possibly sooner if the new Gigabay production facility becomes operational. This speculation was backed up by comments from Lisa Watson-Morgan, the NASA official overseeing the Human Landing System program. She confirmed that SpaceX's V3 prototype will be the one used for orbital refueling tests, specifically because it includes design features for propellant transfer. The twin valves seen in the new section could be among those features. If everything stays on track, SpaceX could be ready for its first in-space refueling demonstration as early as late 2025. For that mission, they will need at least 2 operational prototypes, one to act as the fuel tanker and the other as the receiver. So, what do you think? Will SpaceX launch its refueling mission this year, or will it slip into early next year? Let us know by commenting yes or no down below, with yes being this year and no being next year. And if you're as excited as we are to see the future of space travel unfold, be sure to like the video and subscribe to Great SpaceX, because we'll keep you updated with the latest on Starship, refueling, and the next era of interplanetary exploration. To make in-orbit refueling a reliable part of its operations, SpaceX must overcome several major challenges, both in terms of vehicle performance and support infrastructure. While recent developments show exciting progress, the road to mastering the refueling system is still filled with technical hurdles. The first and most essential step is for SpaceX to consistently complete the basic phases of a Starship mission: a successful launch, in-orbit operations, and safe return. Each of these milestones is foundational to achieving a refueling mission. Among them, reaching orbit and performing complex tasks such as payload deployment and engine reignition in space are especially critical. These capabilities form the core of what Starship must do before it can even attempt to refuel in orbit. At the moment, SpaceX is facing scrutiny due to issues during ascent in the last 2 Starship flights. Both missions saw anomalies that prevented a fully nominal flight profile, particularly in the early phase of launch. These complications have fueled doubts about whether the company can stick to its aggressive timeline for orbital refueling. That's why the upcoming Flight 9 is seen as a crucial test. SpaceX will need to demonstrate improvements in both launch stability and in-orbit performance to build confidence in Starship's capabilities. Following this, another major milestone will be the successful re-entry of a second-stage Starship, or Ship V2 at this point. A controlled descent and recovery would prove that the vehicle is on track to become not only powerful, but reusable, an essential feature for sustainable space operations. Reusability plays an even greater role when it comes to orbital refueling. The ability to rapidly turn around Starships between missions, rather than building a new vehicle each time, makes large-scale refueling logistically and financially feasible. If SpaceX can land and refurbish its vehicles quickly, the cost and complexity of running a refueling fleet drop significantly. But even after these basic steps are mastered, the challenges of the refueling process itself are far from simple. The first major hurdle is physical connection. If SpaceX pursues a direct transfer model where one Starship refuels another in orbit, both vehicles must be launched within a tight time frame, and then perform a precise rendezvous. They must dock perfectly, transfer fuel while maintaining alignment, and then safely disengage. This operation requires flawless coordination between 2 massive spacecraft in a zero-gravity environment, all while being remotely controlled from Earth. Even slight deviations in trajectory or speed could jeopardize the mission. An alternative would be to construct an orbital fuel depot, essentially a stationary tank in space. This would relieve the pressure of coordinating 2 launches in quick succession. However, launching such a depot is a challenge in itself. The structure would need to be roughly the size of a Starship or larger to store meaningful amounts of fuel. As of now, no rocket can deploy such a massive station in a single launch. That means it would likely need to be launched in segments and assembled in orbit or designed as an inflatable structure. Then, there's the environment of space to contend with. Unlike Earth, space lacks gravity, atmospheric pressure, and the stable conditions engineers typically rely on. These differences make transferring fluids much more difficult. Without gravity to help control flow direction, managing the movement of cryogenic liquids like liquid oxygen and liquid methane becomes a much more delicate process. Temperature control is another major concern. Starship's fuels must be kept extremely cold, at around negative 180 degrees Celsius for methane and negative 207 degrees Celsius for oxygen. Space, while cold on average, is subject to intense fluctuations due to direct sunlight and shadow. Without proper insulation, the fuel could freeze, boil off, or become unstable. Even slight changes in temperature could cause the fuel to vaporize or block the flow, jeopardizing the mission. Lastly, the challenges aren't only in space, they're here on Earth as well. For a single deep space mission, like NASA's Artemis moon landing, SpaceX estimates that at least 10 Starship tanker launches could be required to fuel one Starship in orbit. A Mars mission could demand significantly more. That level of demand puts enormous pressure on production. Starship would need to be mass-produced at a scale far beyond what we see today. Beyond manufacturing, SpaceX would also need a robust testing and support infrastructure. Launch pads, fueling stations, ground crews, and recovery systems would all need to be scaled up. Rapid launches in succession would demand an even faster turnaround of spacecraft between flights. If SpaceX does choose a direct transfer model, that means multiple tankers may need to launch within days or even hours of one another, pushing current capabilities to their limits. In summary, SpaceX's vision for in-orbit refueling is bold and groundbreaking, but it's also incredibly complex. From perfecting flight reliability to building a scalable support system, there are many pieces that still need to fall into place. But if anyone can solve these problems and redefine space travel, it's the team that turned reusable rockets from science fiction into everyday reality. Despite the challenges ahead, SpaceX has many reasons to be confident. They've already shown the feasibility of using methane in space during the tipping point demonstration on Flight 3. Additional proof comes from other systems using methane, like Intuitive Machines' lunar landers and China's Zhuque-2 rocket. While orbital refueling remains technically demanding, SpaceX has relevant experience. Docking Starships together is conceptually similar to how they've been docking Dragon capsules with the ISS for years. On the production side, the company's Star Factory is now automating mass Starship manufacturing, with the high bay being replaced by the larger Gigabay and a second launch tower nearing completion at Starbase. SpaceX is well positioned to scale operations rapidly. Even if they don't have enough tankers built immediately, Starship's full reusability and rapid turnaround offer a major advantage, allowing for a high launch cadence to support refueling efforts. Momentum is building fast. The approval of 25 launches per year from Starbase, along with the Starbase City project, signals a sharp increase in testing and flight activity. This will help SpaceX reach the milestones required for a working in-orbit refueling system. The rollout of the first refueling hardware is more than just a technical update. It's a clear statement from SpaceX saying they're ready to take on one of their most ambitious challenges yet. Big changes are coming fast. Are you ready to witness them? What are the limits of Starship? That is always the question many people ask when talking about the world's largest rocket, SpaceX's Starship. Designed to be fully reusable and capable of carrying enormous payloads into space, Starship is not just another rocket. It's a potential game changer for humanity's future beyond Earth. Recently, an insightful analysis by a team of top-notch scientists emphasized SpaceX's role as a crucial solution to the deadlock currently facing space exploration in the decades ahead. So how exactly could Starship influence the future of astrophysics and deep space missions? Starship is making consistent progress toward its ambitious goal, including lunar landings under NASA's Artemis program and eventual crewed missions to Mars. But the potential of this vehicle goes far beyond Mars. It could become a fundamental infrastructure piece for science missions across the solar system and even deeper into space. This claim isn't just hype, it comes backed by rigorous scientific analysis. A recent article shared on Fermat's library and on social media platform X brought attention to a compelling analysis led by respected astrophysicist Martin Elvis of the Harvard-Smithsonian Center for Astrophysics, Charles Lawrence of NASA's Jet Propulsion Laboratory, and MIT physics professor Sarah Seger. These scientists argue that SpaceX's Starship could accelerate astrophysics research by decades, a bold claim with significant implications. Their analysis caught the attention of none other than Elon Musk himself, who simply replied, "Absolutely," signaling his firm belief in Starship's transformative power. To understand why such confidence is being placed in Starship, we need to look at what astrophysics need over the next few decades. According to the 2020 Decadal Survey, or Astro 2020, the scientific community has laid out ambitious plans for a new generation of space-based observatories. These include LUVOIR, or Large Ultraviolet Optical Infrared Surveyor, the Origins Space Telescope, and the LYNX X-ray Observatory. Each of these observatories is designed to vastly outperform legacy systems like Hubble and Chandra, which have served science well for decades but are nearing the end of their operational lives. LUVOIR, for instance, would offer high-resolution observations in both ultraviolet and infrared. LYNX would focus on X-ray wavelengths, and Origins would probe far infrared signals to study the birth of stars and planets. Together, these observatories are intended to complement the James Webb Space Telescope, which launched in 2021 and focuses on near and mid-infrared observations. This combination would give humanity an unprecedented view of the universe. However, there's a problem. Many of our current flagship observatories are aging rapidly. Hubble, launched in 1990, has been a workhorse for decades but is now running at minimal capacity. Its mission is expected to end sometime in the early 2030s. Chandra, launched in 1999, is also showing signs of wear and is often on the chopping block when federal budgets are tight. While Webb is still relatively young and functioning well, it cannot replace all the capabilities of its predecessors. This creates a looming observational gap. From around 2030 to 2040, space science could be severely disrupted as aging observatories go offline, while the next generation remains grounded due to funding and logistical challenges. According to current projections, NASA may not be able to launch LUVOIR, LYNX, or Origins until the 2040s or even the 2050s. A primary reason: budget constraints. The significant cuts to NASA's Science Mission Directorate has reduced astrophysics funding from $1.5 billion to just $500 million, a reduction of nearly 2/3. That's where Starship enters the picture. Scientists believe Starship could enable NASA to deploy these next-generation observatories earlier, potentially preserving the continuity of data and scientific discovery. How? It comes down to two major advantages: payload capacity and cost efficiency. Starship is designed to carry more than 100 metric tons to low Earth orbit. This exceeds the capabilities of every existing and proposed launch system, including the retired Delta IV, Atlas V, Ariane 5, current launchers like Falcon 9 and Proton M, and even NASA's own Space Launch System Block 1B. Even more impressively, newer versions of Starship, such as the V3 variant, may increase that capacity to more than 200 metric tons to LEO. Estimates suggest that this version could also deliver around 21 tons to geostationary transfer orbit and 18 tons to the Sun-Earth L2 Lagrange point, a popular location for space telescopes due to its stable thermal and gravitational environment. Starship V3 is expected to launch as early as this year. And that's without considering in-orbit refueling, a future capability SpaceX is actively developing. With it, Starship could carry 100 tons or more of observatory equipment to destinations as far away as the Moon, Mars, or even outer solar system orbits. Then there's the issue of cost. Starship is constructed from relatively inexpensive stainless steel and runs on methane and liquid oxygen, both cheaper and more accessible fuels than those used in traditional rockets. SpaceX's goal is full reusability of both the booster and upper stage, which could reduce the cost per launch to as low as $2 million. That's an order of magnitude cheaper than current rockets, which often cost hundreds of millions per launch. This dramatic reduction in cost could make it feasible to launch large observatories even under tight budgets. Moreover, SpaceX plans to operate Starship frequently with multiple launches per year. This not only provides scheduling flexibility for NASA and private contractors, but also accelerates the overall pace of space missions. One of the most underrated advantages of Starship is its enormous payload bay. The V1 Starship offers about 1,100 cubic meters of internal volume, roughly 18 meters long and 9 meters in diameter. This dwarfs the available space in any rocket ever launched. Future versions missions like V3 may double this capacity, exceeding 2,000 cubic meters. Starship's enormous payload volume allows large observatories to launch fully assembled in a single mission, eliminating the need for complex folding mechanisms, multi-launch assembly, or high-risk in-orbit construction. This greatly reduces both costs and operational complexity. Its gentle ascent and spacious fairing also enable the use of simpler, more affordable materials like glass mirrors instead of costly beryllium, making telescopes easier and cheaper to build. Engineers can then focus more on scientific instruments rather than structural durability, enhancing mission capability and scalability. Together, Starship's payload capacity, low cost, fast launch cadence, and simplified logistics could remove the long-standing bottlenecks holding back astrophysics missions. The scientists behind the Fermat's library analysis urge NASA, academia, and industry to design observatories around Starship's capabilities not just for launches, but for integration, servicing, and even retrieval. They argue that aligning with Starship isn't optional, it's critical. Without the shift, the 2030s risk becoming a lost decade in space science, while global competitors surge ahead. More than a rocket, Starship is a game-changing platform. If SpaceX meets its goals, it could usher in a new era of space science, rapidly deploying observatories that would otherwise remain grounded for decades. The choice is clear. If you believe in Starship's promise, comment absolutely down below. And don't forget to like the video and subscribe to Great SpaceX to stay on top of SpaceX's epic journey. To achieve reliability for future high-stakes missions, SpaceX must first complete the foundational objectives with Starship and do so soon. The window for establishing Starship as the cornerstone of humanity's spacefaring future is narrow, and the tasks ahead are as urgent as they are complex. At the top of the list is mastering in-flight capabilities. Starship needs to demonstrate consistent success through each phase of its mission profile. While Starship made notable strides in 2023, progress has seen some delays this year. Flight 7 and 8, conducted in early 2025, were valuable learning opportunities, but failed to fully meet the performance benchmarks SpaceX is aiming for. That makes Flight 9 and the upcoming test campaigns pivotal. These flights must prove that Starship can carry out its mission objectives from launch to landing. Without that, confidence in using it for lunar and interplanetary missions will waver. On the ground, SpaceX's infrastructure also needs to evolve. The current Launch Pad B at Starbase in Texas has undergone dramatic upgrades, including a redesigned orbital launch mount and the addition of a flame trench to better handle the immense power of Raptor engines. However, one pad alone will not be sufficient for the high cadence of launches envisioned. SpaceX must replicate and expand this model to support frequent missions, including fast turnaround for landings and reflights. If SpaceX proceeds with drone ship landings, especially for missions where a return to Starbase isn't feasible, it'll need a new class of recovery vessels and transport infrastructure. This could require stronger international cooperation, particularly for deploying and recovering starships in global waters or at overseas facilities. The production system also demands significant scaling. The Star Factory, a massive facility under construction in Boca Chica, is expected to revolutionize how quickly SpaceX can manufacture starships and Super Heavy boosters. SpaceX can manufacture starships and Super Heavy boosters. Already, we're seeing the removal of older assembly bays to make room for high-throughput, vertically integrated production lines. But Texas alone won't be enough. Expansion into Florida's launch facilities, where SpaceX will support Artemis and other NASA programs, is critical. These sites must match or exceed the capabilities of Starbase to ensure mission redundancy and consistent output. Testing infrastructure must also grow. The current Massey Test Site is too limited in scale to handle the next phase of development, which includes propulsion testing, tank pressurization, heat shield validation. As the complexity of the Starship program increases, so must the facilities that support it. The flame trench and deluge systems, which, while critical to each launch, must be adaptable and replicable at new sites. Once Starship's core systems are reliable, SpaceX will begin testing orbital refueling, essential for Moon and Mars missions, by late 2025 or early 2026. Without it, long-duration crewed flights would be impossible. The real test will come with major missions later this decade. Artemis 3, planned for 2027, will return astronauts to the moon using Starship as NASA's human landing system. A successful landing would confirm Starship's capabilities and reaffirm U.S. leadership in space. Next come Mars missions, both robotic and crewed, laying the groundwork for a multiplanetary future. Success here will boost SpaceX's credibility in deep space science missions as well. Beyond exploration, Starship could serve military and government needs thanks to its vast cargo space and rapid deployment ability. Ongoing use would ensure steady revenue and valuable flight data. Starship's edge lies in its powerful mix of features: massive payload capacity, fast turnaround, full reusability, and dramatically lower costs, potentially cutting launch expenses to a fraction of today's rates. The Starship moon missions are getting closer. Before landing astronauts on the moon for NASA's Artemis program, SpaceX will first perform an uncrewed demonstration flight. What makes this mission stand out? NASA recently confirmed it will fly without a payload, prompting debate.
We are not sending any payloads on that mission.
Why send a rocket all the way to the moon without cargo? Is it a missed opportunity for science or supplies? In today's episode of Great SpaceX, we'll break down NASA's reasoning, explore whether this approach makes sense, and ask if there is a smarter alternative. We are nearly halfway through 2025, and that means one thing. The long-awaited mission to return humans to the moon is fast approaching. This historic event is currently assigned to Starship, the world's largest and most powerful rocket, developed by SpaceX. But before astronauts board for that journey, critical testing must be completed. That includes an uncrewed mission designed to demonstrate Starship's ability to reach and land on the moon. This uncrewed mission is vital. It'll serve as a rehearsal for the actual crewed landing, giving NASA and SpaceX a chance to validate key systems and operations. However, many have been asking an important question. Will this demo flight carry any additional payloads? Surprisingly, that question was recently answered by NASA officials. In a session with the Lunar Destinations for Human Explorers Steering Committee, Lori Glaze, acting Associate Administrator for NASA's Exploration Systems Development Mission Directorate, revealed that Starship HLS, which is short for Human Landing System, will not carry any payloads during its uncrewed landing demonstration. On the one hand, this announcement confirms that the uncrewed demo is indeed happening, which is great news, but on the other hand, the decision to launch a mission to the moon without utilizing Starship's enormous payload capacity has left many scratching their heads. Why would NASA miss an opportunity to deliver scientific instruments, experiments, or even a small rover to the lunar surface, especially when Starship is capable of carrying far more than any previous lander? If we're trying to understand NASA's reasoning, one likely explanation is risk. This is, after all, the first time the Starship HLS will attempt a full moon landing. NASA may be avoiding additional complications that could arise from carrying a secondary payload. In short, they don't want to jeopardize the success of the demo mission by introducing new variables. That said, there's one canceled project that many believe would be perfect for this kind of mission: Viper, or the Volatiles Investigating Polar Exploration Rover. Originally, Viper was scheduled to launch aboard a SpaceX Falcon Heavy rocket as part of the Griffin mission. Its job was to explore the moon's south polar region and map water ice deposits, an essential step in preparing for future human missions and permanent lunar bases. But in July of 2023, NASA abruptly canceled Viper, citing a desire to save $84 million. This decision was widely criticized, not just because of Viper's scientific value, but also because of the math. NASA had already spent over $430 million building the rover and was planning to spend another $236 million to operate it. Scrapping the project just to save a relatively small amount looked wasteful, especially considering that Viper had already been built fully and was entering final environmental testing. NASA later invited private companies to propose new ways to get Viper to the moon, but on May 7th of this year, the agency announced that it had canceled that initiative as well. They thanked companies for their proposals, but offered no alternative path forward for Viper. As it stands, the rover is mothballed, with its parts potentially destined for other missions. But what if there were a better option? Launching Viper aboard the uncrewed Starship HLS demo could be a smart way to salvage the mission and unlock scientific value without incurring additional launch costs. Viper itself is relatively small, about the size of a golf cart, measuring by 1.5 by 2.5 meters and weighing just 430 kilograms. For Starship, which is built to carry over 100 metric tons, this would be a negligible addition. Starship has ample room to spare. Even while focusing on testing its landing capabilities, it could easily accommodate a payload like Viper without impacting the primary objectives of the demonstration. From a financial perspective, this makes sense. Since the demo mission is already funded, NASA would effectively get the launch of Viper for free, addressing the budget concerns that initially led to its cancellation. For SpaceX, including a payload like Viper would also serve as a valuable systems test. It would offer an opportunity to trial cargo deployment operations, an essential step for future missions involving crew equipment, habitats, and scientific instruments. NASA's reluctance may come down to the ongoing operational costs, which involve maintaining mission control, supporting Viper's communication systems, handling data, and managing the science. However, these expenses could be well worth it given Viper's potential to map lunar ice, guide future exploration, and support America's long-term strategy on the moon. There's another important point to consider. NASA has not said other payloads can't fly on the uncrewed Starship mission. Their statement only ruled out agency payloads, meaning private companies or even SpaceX itself could still choose to include secondary hardware. However, Viper remains a uniquely well-suited candidate. Already built, scientifically valuable, and ready to go. So, here we are. NASA has a nearly complete rover that was canceled at the last minute, a massive lunar lander flying without cargo, and a moon program in need of momentum. The question now is, should NASA reconsider its decision and allow Viper to fly aboard Starship's demo mission? Let us know what you think with a yes or a no down below, and share your thoughts in the comments. Should NASA take advantage of this rare opportunity, or is playing it safe the right call? One thing's for sure, the moon is calling, and every mission counts. It's becoming increasingly clear that NASA's decision not to include payloads like the canceled Viper rover on the uncrewed Starship HLS test flight is just one part of a broader issue within the Artemis program. Despite aiming to return humans to the moon and establish a long-term presence, NASA continues to struggle with cost overruns, outdated systems, and shifting priorities. While relatively low-cost, high-potential projects like Viper have been cut under the guise of saving money, billions are still funneled into legacy programs like the Space Launch System, Orion spacecraft, and Lunar Gateway, each plagued by delays, technical issues, and massive costs. SLS, rooted in early 2000s programs, has taken decades and over $11 billion to develop, yet has only flown once on Artemis 1 in 2022. Though successful, the mission came at a steep cost. Artemis 2, SLS's next flight, has been delayed repeatedly and isn't expected before April of 2026. Beyond delays, concerns about SLS's reliability for crewed missions and its heavy infrastructure demands have made it a controversial cornerstone of the Artemis program. Orion, another Artemis pillar, also faces setbacks. After returning from Artemis 1, engineers discovered heat shield damage, sparking a 2-year investigation that delayed further preparations. Only recently has Orion been cleared for integration with SLS, but doubts remain about its readiness and cost-effectiveness. Yet NASA continues to defend these systems despite growing concerns. However, that may change soon. A recent White House proposal suggests canceling both SLS and Orion after Artemis 3, marking a major potential shift in NASA's lunar strategy. The Lunar Gateway has also drawn criticism. Intended as a modular station orbiting the moon to support crew and cargo transfers, Gateway adds significant complexity and cost. It also appears incompatible with SpaceX's Starship HLS, which is designed for direct lunar landings. Acknowledging this misalignment, NASA has recently decided to cancel Gateway, signaling a broader shift away from inefficient legacy infrastructure. These moves suggest NASA is approaching a turning point. The commercial space sector, led by companies like SpaceX, is proving that faster, cheaper, and more adaptable solutions are possible. Instead of investing in aging systems, NASA could support smaller, high-impact missions like Viper, which was nearly ready for flight and cost only $750 million. Its mission, to map lunar ice crucial for future habitats and fuel, offered direct value to Artemis goals at a fraction of the cost of programs like SLS or Orion. Refocusing on agile, science-driven missions could boost Artemis's efficiency and public support. With delays mounting and budgets tightening, strategic changes aren't just sensible, they're necessary. NASA must rethink its priorities. Rather than clinging to bloated, underperforming systems, it should embrace innovative, cost-effective programs that can get us back to the moon and beyond, smarter and faster. SpaceX must now accelerate Starship's development to meet the ambitious timelines of the Artemis program. When compared to NASA's own launch systems, Starship clearly demonstrates significant potential. Its massive size offers the capability to transport large payloads and crew members, while its innovative design introduces possibilities far beyond a single-use rocket. In the future, Starship could even serve as an orbital station or semi-permanent base on the moon. However, there's still much work to be done before those visions can become reality. Over the past 2 years, Starship has reached several impressive milestones, most notably the ability to land its booster stage using the mechanical arms of the Mechazilla Tower. But challenges remain, especially with the second stage, which has experienced failures in its last 2 test flights. To stay on track, SpaceX must now focus on improving several core flight systems. These include mastering stage separation, orbital maneuvers like payload deployment and engine reignition, as well as safely executing reentry and landing procedures. The upcoming Flight 9 will be a critical test in that sequence. Simultaneously, refining the Mechazilla recovery process for the upper stage will be key to achieving full reusability, one of Starship's most important advantages. Beyond these technical goals, SpaceX must also begin full-scale development of the in-orbit refueling system. This system is essential for future long-distance missions, including the Uncrewed Starship HLS landing demo and eventually for the Artemis III mission. Alongside that, the company must finalize and test the human landing system variant of Starship to support both the uncrewed and crewed lunar landings. Despite the complexity of these tasks, there are reasons for optimism. SpaceX has recently received approval to conduct up to 25 Starship launches per year. This increased launch cadence will allow for rapid testing, iteration, and progress. With each flight, SpaceX moves closer to qualifying Starship HLS for its vital role in landing humans on the moon for the first time since Apollo. The first HLS missions, especially the uncrewed one, will be crucial not just for testing but also for setting the stage for future lunar exploration. These missions present valuable opportunities for NASA and SpaceX to optimize mission planning, demonstrate key technologies, and even consider the addition of payloads that could enhance scientific return. With smart, forward-thinking decisions, both agencies can maximize the effectiveness of every launch and bring us one step closer to humanity's return to the moon. Without SpaceX, which company is best positioned to lead the future of aerospace? While names like Blue Origin or ULA often come up, Rocket Lab is quickly emerging as a serious contender. Its steady progress and recent achievements have even outpaced some of the industry's bigger players, making Blue Origin look slow by comparison. With the upcoming debut of its next-gen rocket Neutron, Rocket Lab is poised to widen that gap. So how is Neutron shaping up, and what makes it a potential game-changer? Rocket Lab has rapidly risen to become the second most active private space company in the world, surpassed only by SpaceX. Since the debut of its Electron rocket in 2017, the company has successfully launched more than 60 orbital missions, reaching a peak of 14 launches in a single year. This is an impressive feat for a company that entered the space industry after major players like Blue Origin and United Launch Alliance, a joint venture between Boeing and Lockheed Martin. What makes Rocket Lab's story even more remarkable is that it has achieved this level of success without the backing of a billionaire founder. Unlike its larger competitors, Rocket Lab's growth has been fueled primarily by innovation, efficiency, and a focused business strategy, rather than deep financial resources. In the short term, Rocket Lab plans to continue expanding its capabilities of its Electron rocket, which is already a reliable vehicle for delivering small payloads to orbit. However, the company's long-term vision goes far beyond small satellite launches. It is now developing a much larger and more powerful launch vehicle named Neutron. which is expected to play a major role in the medium-lift launch market. If successful, Neutron could dramatically shift the competitive landscape and even challenge the pace of development at Blue Origin. While Jeff Bezos' company has taken over 2 decades to develop and prepare its New Glenn rocket for launch, Rocket Lab aims to complete Neutron's development in just about 5 years. That stark contrast highlights Rocket Lab's commitment to fast, efficient engineering, as well as its ambition to move quickly in a highly competitive industry. Neutron's design also sets it apart from other rockets in development today. Standing at 42.8 meters tall, Neutron is relatively short compared to other medium-lift rockets. However, it makes up for this with a wider body, expected to measure between 5 to 7 meters in diameter. This stout, robust form factor is tailored to support large payloads while keeping the overall rocket compact and efficient. One visually distinctive feature of Neutron is its black exterior, a stark contrast to the white or metallic finishes seen on most other rockets. This dark color is part of a deliberate design choice that reflects both function and aesthetics. The rocket's body is made from carbon composite materials, a lightweight yet strong and heat-resistant option that is well suited for surviving the intense conditions of atmospheric re-entry. Another major innovation lies in Neutron's emphasis on reusability, a principle that has become essential for reducing the cost of space access. Rocket Lab has introduced a groundbreaking feature in the rocket's first stage, a special integrated fairing system known internally as the Hungry Hippo. Unlike traditional rockets, which eject their fairings mid-flight and let them fall into the ocean, Neutron's fairing only partially opens to release the second stage. It remains attached to the rocket and closes again, returning to Earth with the booster. This approach offers multiple advantages. It eliminates the need for separate recovery systems for the fairings, simplifies the overall vehicle design, and avoids damage caused by saltwater exposure. Additionally, this configuration offers better protection for the second stage, ensuring it remains intact and ready for its portion of the mission. For landing, Neutron will use fixed landing legs, referred to as static landing legs. These legs don't fold or retract, which significantly simplifies the rocket's mechanics. By removing moving parts, Rocket Lab reduces the chance of mechanical failure, lowers production complexity, and shortens turnaround time for refurbishment and reuse. To further support a precise landing, the rocket will feature aerodynamic control fins near the upper portion of the booster, just below the fairing. These fins can rotate during descent, helping guide the booster to a safe touchdown. Currently, Neutron is still in the development and production phase, but Rocket Lab expects to roll out the rocket soon in preparation for its first flight. Neutron's second stage introduces yet another unique feature. Instead of being mounted on top of the first stage as in most traditional designs, it is housed within the first stage's fairing like a payload. This configuration provides added protection during ascent and allows for a lighter second stage structure. The lighter design, in turn, improves overall flight performance and fuel efficiency, helping the rocket carry heavier payloads farther into space. Altogether, Neutron represents Rocket Lab's bold step into the future of spaceflight by combining efficient design, advanced materials, and a long emphasis on reusability. Rocket Lab is positioning itself as a serious contender in a market long dominated by larger and wealthier players. If Neutron performs as expected, it may not only rival Blue Origin, it could redefine what's possible for new generation rockets. To further enhance the capabilities of Neutron's second stage, Rocket Lab has developed a unique satellite deployment system known as Flatellite. As its name suggests, Flatellite is designed with a flat, compact structure that allows multiple units to be stacked efficiently within the rocket's payload bay. This configuration not only maximizes the number of satellites that can be deployed in a single mission, but also enables quicker, more cost-effective launches for customers looking to build or expand satellite constellations. However, this approach comes with a trade-off. The structural modifications required to support Flatellite reduce the potential for the second stage to be reused. While this prevents Neutron from achieving full reusability at this stage of its evolution, it still demonstrates Rocket Lab's long-term focus on making spaceflight more sustainable and economical. With this partial reusability and its cost-efficient launch strategy, Rocket Lab aims to offer Neutron missions in the price range of 50 to 55 million US dollars, significantly lower than many of its competitors in the medium lift market. Development has been moving swiftly. The second stage has already been produced and successfully passed its qualification tests as of early April, marking a major milestone in the path to flight readiness. At the heart of Neutron's propulsion system is Rocket Lab's custom-designed Archimedes engine. This engine uses a combination of liquid methane and liquid oxygen, commonly referred to as methalox, a modern and efficient fuel mix favored for its cleaner combustion and compatibility with reusable systems. After extensive evaluation, Rocket Lab settled on an oxygen-rich closed-cycle combustion process for Archimedes. This configuration increases efficiency by redirecting excess gas into the combustion chamber, boosting overall performance. The Archimedes engine is designed to produce 74.8 metric tons or 165,000 pounds of thrust at sea level and up to 90.7 metric tons or 200,000 pounds in the vacuum of space. It'll deliver a specific impulse, or a measure of fuel efficiency, of 329 seconds at sea level and 365 seconds in vacuum conditions. Neutron will be equipped with 9 Archimedes engines, resulting in a total liftoff thrust of approximately 673.2 metric tons. While these performance figures may appear modest compared to some larger rockets, they align perfectly with Rocket Lab's mission to keep Neutron simple, efficient, and fast to produce. The use of carbon composite materials throughout the rocket contributes to this simplicity. These materials are not only lightweight and strong, but also heat-resistant and compatible with high-speed manufacturing processes. Rocket Lab plans to use automated systems to produce carbon composite components, potentially creating large rocket sections within minutes, a production speed that could revolutionize the industry. The first Archimedes engine test campaign, conducted in January, delivered highly encouraging results. The engine exceeded expectations by operating at 102% of its rated power, showcasing both the strength of the design and the quality of the engineering team behind it. To complete the Neutron system, Rocket Lab has also developed a vertical landing system for the first stage. Much like SpaceX's Falcon 9, Neutron is designed to return to Earth and land vertically, enabling reusability and rapid turnaround between launches. For recovery, Rocket Lab will utilize a floating offshore platform, conceptually similar to SpaceX's drone ships. However, this barge will be customized to accommodate Neutron's structure and landing dynamics. By landing at sea, Rocket Lab can extend the rocket's downrange performance while keeping recovery operations efficient. What's particularly bold is that Rocket Lab plans to attempt this landing maneuver on Neutron's very first flight. It's an ambitious move, especially considering the technical challenges involved. For reference, Blue Origin also attempted a drone ship landing with its New Glenn booster on a maiden flight and did not succeed. However, Rocket Lab brings an advantage to the table. It has already conducted multiple splashdown recovery tests with the smaller Electron rocket. These missions have given the company valuable hands-on experience with booster re-entry and retrieval, building a stronger foundation for Neutron's success. Altogether, Rocket Lab's Neutron project reflects a company aiming high and moving fast. From the innovative flatellite system and advanced Archimedes engines to full carbon composite construction and reusability features, every element of Neutron has been designed with ambition and practicality in mind. While beating SpaceX outright may not be realistic in the short term, Rocket Lab is well positioned to outpace other competitors like Blue Origin in terms of speed, innovation, and cost efficiency. So, do you think Rocket Lab and its Neutron rocket can surpass Blue Origin and New Glenn? Let me know with a yes or a no down below and tell me why. Also, like the video and subscribe to stay updated on Rocket Lab, SpaceX, and the evolving world of space exploration. Anyways, with all preparations underway, Rocket Lab is gearing up for a major leap forward. The company is targeting the second half of this year for Neutron's first launch, now just months away. To meet that goal, Rocket Lab must soon finalize and assemble all major components, especially the distinctive first stage booster. Once the rocket is complete, it will undergo critical tests such as static fire and a wet dress rehearsal. This debut mission will likely fly without a payload, allowing full access on validating Neutron's performance. Its success is crucial, not only to establish Neutron's credibility, but also to pave the way for future contracts and commercial growth. In fact, Rocket Lab has already secured its first Neutron customer, announced at the end of last year. While the client remains undisclosed, the company has committed to 2 Neutron launches in 2026 and 2027 to serve this partner. These missions will mark Neutron's entry into the competitive commercial launch market. This has been Kevin with Great SpaceX. Don't forget to like the video and subscribe if you haven't already to stay up to date with yours truly in the latest details of SpaceX's progress. Thank you so much for tuning in, and remember, curiosity, imagination, and inspiration will always follow you as long as you keep looking up.